Good evening. Today I will talk about examining the rod of the heat conduction trainer device made by me, Abdullah Bashar, and my partner Haidar Saad, and presented to Dr. Ansam Adil. And for today, I, Abdullah Bashar, will be the presenter of the subject. Now first, let's take an introduction for the subject. Heat conduction is the heat transfer between molecules under the influence of temperature difference, and it is one of the three basic ways of heat transfer: conduction, convection, and radiation. Heat conduction test bench is a training and teaching device used in the laboratory to study steady state and non-steady state heat conduction. The bench is composed of two parts, a heating part and a heat dissipation part, with cylindrical samples made of different metals inserted between them. Each sample is arranged with 12 temperature measurement points to measure the center temperature of the sample. The design principle of the measurement points is to have as little impact on temperature measurement as possible. The heating part is heated by an electric heater, and the temperature is kept constant during the experiment through a thermostat. The heat dissipation part is realized by a water cooling circuit. The top water tank can adjust the cooling water flow to control temperature changes. For the device now, the photo on the right is taken from the internet for the device, and it is called heat conduction trainer. And for the photo in the left, it is taken directly from our laboratory, the Heat Transfer and Thermodynamics Laboratory in our beloved college. The survey and the examination of today's subject is about the vertical metal rod of the device, which is there on the right, this metal rod, exactly this metal rod. Now for the study. In piping processes, it is very important to assure that the pipe will hold out against the temperature of the water or any other liquid which is traveling inside through the pipe. So, for the plumbers and exactly the pipe's laying workers, they need to select the suitable pipe specifications for the situation. For example, corrosion resistant, pressure problems, depth of pipe, temperature resistant, and others. For the subject of today, we will talk about, in the first order, about temperature resistance, because it is about the third case of heat transfer through a pipe. In this study, we work according to that the law of heat transfer achieves the requirements. So the equation is C square multiply partial square T over partial Z square equals partial T over partial small t. So in the solution process, we will try to find temperature T, x to T, and the initial temperature will be written as function of x, and x equals 0 and x equals L, and solve them as in insulated situation. The solution will rely on the heat flow equation by separation of variables. Now, for the solution, also of course by using separation of variables, it is C square partial square T over partial Z square equals partial T over partial small t. T Z to T equals Z multiply T. C square Z power 2 over Z equals T over T, and equals H we call it h. It is an important note that we dismiss case 1 and case 2 and start with case 3 because it is the case which satisfies our requirements. Now h equals k square z power 2 minus c square z equals 0. By solving the differential equation we get z equals c1 sine k square z plus c2 cosine k square z. This is the first equation, and for the second equation we start with t power 1 equals c square k square t, and by solving the differential equation we get t equals c3 exponential power minus k square multiply c square multiply t, and this is the second equation. Now for the boundary conditions, the first boundary condition is t 0 to t equals 0 and t L to t equals 0, and for the initial conditions is t x and 0, which means x to 0 equals t naught. Now z equals c1 multiply sine multiply k square multiply z plus c2 multiply cosine multiply k square multiply z, all combined multiply c3 multiply exponential power minus c square k square t. Now we start solving for the boundary conditions. For the first one, 0 equals c1 multiply 0 plus c2 multiply L. This will lead to c2 equals 0. For the second boundary condition, 0 equals c1 multiply sine multiply k multiply L. This will lead to c1 doesn't equals 0. And for the k we take it as k equals n multiply pi all over L. Now we begin with the z. Z equals the sum from 1 to infinity for bn. Bn multiply sine multiply n pi over L multiply z multiply exponential power minus c square multiply n square pi square all over L square multiply t. And for t naught equals bn sine n pi over L multiply exponential power minus c square multiply by n square pi square over L square by 0, which is all equals to 1. For all equals to 1, this one. Now for the t naught equals bn multiply sine multiply n pi over L. We will multiply this equation by sine n pi over L z. So it will lead to t naught sine n pi L over L by z equals the sum from 1 to infinity bn sine square n pi over L z. And by integration for both sides, bn equals the integration from 0 to L sine n pi over L by z t naught partial z over the integration of 0 to L sine square n pi over L z partial z. and for final solution and the final answer of the separation of variables we will need is t z to t equals the sum from 1 to infinity integration from 0 to L sine n pi over L z to partial z to as means as t naught partial z over the integration 0 to L sine square n pi over L z partial z all by sine n pi over L multiply z multiply exponential power minus c square multiplied by n square multiplied by pi square all over c square and in the final multiplied by t. At the end, a special thanks to Dr. and Sam and for the audience.